Alright, so today I'm going to be explaining this important paper with the title Diverse Message Passing for Attribute with Heterophily. This NeurIPS paper in 2021. Most of the existing GNNs can be modeled via the Uniform Message Passing framework. This framework considers all the attributes of each node in its entirety, shares uniform propagation weights along each edge, and focuses on the uniform weight learning. The design of this framework possesses two prerequisites: the simplification of homophily and heterophily to node-level property, and the ignorance of attribute differences. Unfortunately, different attributes possess different characteristics. So the network homophily in this paper, the network homophily rate defined with respect to node labels, is extended to attribute homophily rate by taking the attributes as weak labels. Based on this attribute homophily rate, we propose a diverse message passing framework which specifies every attribute propagation weight on each edge. Besides, we propose two specific strategies to significantly reduce the computational complexity of DMP to prevent the overfitting issue. By investigating the spectral characteristics, existing spectral GNNs are actually equivalent to a degenerated version of DMP. So when we have a graph neural networks, we have aggregation and update, which is combined. And so we can summarize it like this. But this formulation can be regarded as uniform message passing, where all attributes which are propagated from node V to node U share the common weight C sub UK. As you see, all of them share the same weight. So it's a uniform message passing. Then all attributes can be aggregated with the same weight assignment scheme in local neighborhood. But since aggregation can be interpreted from perspective of Laplacian smoothing and low-passing filtering, the same weight assignment scheme indicates that all the attribute tends to share similar distribution over the entire graph. To investigate the distributions of attributes and measure their similarity, the attribute homophily rate is proposed. The network homophily rates, including both node version and edge version, quantify similarity between the connected nodes. The node similarity in network homophily rate is measured according to the node labels. The attribute homophily rate is defined by measuring the node similarity according to each attribute. Specifically, the attribute homophily rate of attribute F is defined like this. Figure 1 shows the distributions on networks with different homophily. So to achieve diverse aggregation, this uniform message passing is revised to make different attributes possess different propagation weights. So the scalar C sub Vk that I showed you is augmented to vector C, which has the same length as the node representation H. So each element stands for the weight of the corresponding attribute. And this is just the element-wise product of the vectors. There are two strategies to reduce the number of learnable parameters. The first strategy constrains all the parameters to be defined by a learnable function. The second strategy simplifies this equation, this 4, by assuming that all the neighborhoods employ identical propagation vector. GNNs originate from spectrograph theory, where ChebNet and GCN are two representative methods. ChebNet, which is in reference 24, utilizes Chebyshev polynomials of Laplacian matrix to define the graph convolution. The GCN force the two terms in this equation 8 to share the same mapping function. In fact, the attribute weight C that I showed you in the previous slides cannot be integrated into mapping parameter WK, because those weights tend to be different on different edges and different nodes. Hence, diverse message passing may break the performance ceiling of spectral GNNs. Then they have some theoretical work to support their work. Then they see how they can use their approach for alleviating the oversmoothing issue, which is a real challenge in GNNs. Then they use it for these datasets like Squirrel and Chameleon and other datasets. So they reported their mean classification accuracy. For example, they compare graph SAGE with their method, or graph convolution, or graph attention.